Hello Internet! In this video we are going to take a look at simulating physics in our projectiles. So in a previous video on doing rigid body projectiles where we used a rigid body to actually simulate a projectile, one of the questions that came up was how would you add, say, realistic things, so say gravity or wind or things like that. And really using rigid bodies, there's no good way to do that, or at least not that I can think of, because you really want something predictable, because that way you can kind of predict where the thing will go. If you have a really basic mathematical formula, like a bullet drops 9.8 meters per second or accelerates downwards at 9.8 meters per second, you can plug that in and actually calculate how it will travel and actually predict where it will land at any given distance just based off that and how fast it's moving. So that is sort of why we're moving away from that and kind of bringing in this new strategy. So what I'm going to do is create a projectile. And what it's going to do is it's going to have a speed, which I know nothing about bullets at all. So we're going to guess here. So we're going to say velocity equals 400, and that sounds really slow. Sure, 420 meters per second, which I don't know if that's accurate or not. I don't really have any idea, but that's just what we're going to use. Next, we're also going to add an integer, and this is going to be prediction steps per frame. And I'm going to use, say, 6. And so the idea here is we want to draw an arc, and we want to update that. We want to update that over time. So as our bullet moves, we're going to step forward 6 times and kind of do an arc with 6 arches. In each of those little lines that make up that arc, those are going to be raycasts. So if you want less precision, you lower this down. If you want more, you increase it. You could also change this to be by how far it's actually moved. So take this velocity, multiply it by the time delta, and then divide it by like a total amount moved, and then just take like the ceiling of that. That would give you something based off of how far it moves, so you have something that's more predictable based off of, it's more accurate based off of the distance. I don't really know which one is better, so we're just going to do it this way, and you guys can update it to do whatever you want. So the next thing that we're going to want is going to be a vector 3, which is going to be our bullet velocity. Let's say speed. Speed seems like a good answer here. And so our speed actually, do we need that here? I'm going to include it for now, simply because it makes these calculations easier if everything is kind of contained. But we could actually have that speed be set by the gun that it's being shot out of. So different projectiles, maybe you have the same type of ammo. It will have the same settings or whatever, but the muzzle velocity, the exit velocity may be different. I'm totally making this up. I am not very informed about guns, but I would assume that different guns shoot a similar projectile at different rates. Anyway, what we're going to do is set our bullet velocity equal to our forward vector and multiply it by our speed. And so this gets us a direction of our bullet and a speed that it will move at. So initially, there's no downward momentum, there's no gravity that's affected it, there's no wind or anything like that. We can add all of that later. So now that we have that, let's jump into on draw gizmos. All right, and so what I want to do is grab a start position. We'll just call it 0.1. And that can just initialize to our current position. And so we're going to iterate for each variable. How do I want to do this? So effectively what we want to do is actually step this bullet through time multiple times in that single frame. And so we're actually taking a subset of the time and getting whatever we get. For this, we're going to simulate how far it would go in, say, a second. I don't know if that's a good idea or not, but that's sort of what we're going to do. So we're going to say our step, for our step, let's say while the step is less than 100. Actually, it makes more sense to do less than 1. And let's make this a float, like so. And we are going to add, since we're doing a second, we're actually going to, over the course of this, we are going to add 9.8 meters per second over time to that acceleration. So, yeah, I think linearly sounds like it would work for this. But we'll see if that works. There's going to be 100 steps in this loop. This is strictly for debugging. Nobody will see this in game, and nobody's going to actually like test this. But what this is going to do is just step it over time, 100 steps, and actually create these points. So let's create that second point. It's going to equal 0.1 plus, what is it going to do? Plus our bullet velocity times the step. So we're actually multiplying, using the step as sort of the time scale and sort of stepping forward that way. And then after we have that, we just need to connect those two and set 0.1 equal to 0.2. This isn't going to work because we're not updating for gravity, but that can come later. So this should just draw a straight line out of 100 line segments for now. So let's color this, say, red, just so we can pick it out a little bit easier. And then gizmos, draw a line from 0.1 to 0.2. And then set 0.1 equal to 0.2. And then this will just keep stepping forward. So we should see a line 420 meters long. Assuming I did everything correctly. And Unity doesn't crash, apparently, because that seems to be what's happening right now. Come on, there we go. Well, we have no bullet velocity, so let's do 420. There we go. That is a very long line. That is also a very long line. Why is it so long? It shouldn't be that long. Oh, ha. Because we don't want to multiply by this bullet velocity, we want to multiply by the step size, 0.01 f. Otherwise, it's exponential increase over time. So it'd do 0.1 and then 0.2 for the next time, and since we do that 100, that actually gets really big. So that's where that problem was coming from. So yeah, there we go. This should update and jump down to a reasonable thing eventually. For some reason, compiling has been taking a long time. I need to rebuild my computer. It's been a while. This hardware is 3, 4, some of it's 6 years old. So we'll need to do that eventually. Anyway, it's working. We can actually draw our line now. The problem is we're not updating our velocity. And so what we're going to do is we actually have a step size. So we're going to say our bullet velocity plus equals our physics dot gravity times 0.01, our step size. That's sort of what we're multiplying this by. So let's actually rename this to our step size, because we're going to be reusing this code. That's sort of why we're doing all of this. We're doing all of it here because this way when we move it to using raycasts and you can't really tell what's going on, we'll still be able to reuse all of this. And actually, this Gizmo code is going to more or less duplicate exactly what the Rigidbody version or the Raycast version is going to do. So we plug in the step size. We're now updating our physics. I'm also going to update or store a local copy of this bullet velocity so we don't update it when we draw our gizmos, because that will just break everything. So we're going to call it our temp bullet velocity, or let's call it predicted bullet velocity, and set that equal to our bullet velocity. Pull that in here and there. And so that's just used for all of our calculations, and then it can get discarded because this is just a gizmo. We don't actually need that for much. So now there should be a little arc to this. This might be a little bit long, so we may not actually see much. But 420, so it should drop theoretically 9.8 seconds. And you can kind of see it. If you go here, you can see it drop off at the end. It's an exponential increase because gravity. So it will have more effect at the farther ranges. So if I reduce this for whatever reason, say 20, it's using the bullet velocity as the prediction. So it's predicting it'll move 20 meters and drop 9.8 in this second. And so that will look something like this. And so that's kind of giving you a prediction of where it lands. And so what we need to do now is actually take this model here and actually predict this. So if you have really fast moving projectiles, like say this is like multiple thousand, it's really not going to work for rigid bodies, and you actually may need to know, I guess, if it's falling. I don't really know if we need all of these like subframe arcs. That may be overkill. We may not actually need it. But for the sake of precision, or just for the sake of demonstration, we're going to do it this way. You should be able to drop it to 1 and it should just work. So there's not much problem there. So yeah, what we're going to do is do a vector 3, 0.1, and grab our position. This should look really familiar because it's literally the exact same. The only thing we're not going to do is update our velocity. So we're not going to have a predicted velocity. We're actually going to update the velocity here. Then let's do a step size. And this is going to be 1 or, this is going to be our time delta time divided by our prediction steps per frame. So there are however many steps per frame in this. Is this a good way to do this? This might be a really bad way. Let's do 1.0f instead. And so this way we can just count up to 1 again, but our step size is different. It's based off of this number and not 1 to 100. Then let's do our for loop. I guess we can copy and paste since we're literally just copying. And let's update our bullet velocity. We could also swap out this line for some more complex physics simulations. So if you want to stick in wind, for example, if you want wind to affect this, or maybe add drag to the bullet so it slows down as it goes, this is where you could add that. And everything would just behave as you would expect. We're not going to do that because that's just making things more complicated. We don't need to worry about that. So let's plug in our step size here for our point. And instead of this Gizmo's draw line, we're actually going to want to do a raycast and do some sort of callback. But we're moving too far. This whole increase needs to be modified by our time delta. So the physics increase needs to be multiplied by that time delta, as well as that. So this changes both of our points to be calculated based off of that delta time instead of predicting a full second. If we didn't do that time delta, it would cover a full second, and that's too much in a frame. It would just go way too fast. So now we're here. Time for some physics stuff. So we have a ray that we can create. What do we want to do? Ray. Let's create a new ray from point 1 in the direction of 0.2 minus 0.1. I guess that works. This part may not be optimal. There's a lot of tinkering that we could do to probably make this a little bit better. That's not really the concern here. It's more talking about the physics and how you would add gravity to this whole thing. And so if I do a physics raycast, let's plug in our ray, and then the max distance is actually going to be 0.2 minus 0.1, and we're going to grab the magnitude off of that. So 1 sec, that's totally wrong because parentheses, and then we can close that off. And if we end up in here, we have hit something. So we can do debug dot, what do we want to do? I guess we'll say hit. That is probably the most anticlimactic way to handle this, but it will work. So here's our projectile. Let's add a sphere onto it. That is a massive sphere, but oh well. And we have this fancy prediction, so we actually already know where it's predicted to land. So I should just be able to drop a cube somewhere along this path. As long as it intersects the path, and assuming our prediction is correct, we should get a hit. So something like this. It's going to hit it in less than a second, so that may be a little bit against us, but oh well. I'm going to update the speed because that's actually where we set this bullet velocity. Our start actually initializes it. But I should be able to start this, so if I pull our game over like so, and then start this, we should see it fly. We're not actually moving it. That would be important, wouldn't it? Oops. So we can update the position here to the second point. No, we're not going to do that. We're at the very end. We're going to take point 1, and that's going to be our new position. And so point 1 will be set because down here, point 2 sets it, and then we'll just grab that as our final position, and hopefully that actually updates it instead of just being wrong. So this should give us an arc, and we get to hit once. I'm actually going to run this paused so we can actually have a little bit of a better idea of what's going on here. But our console is empty. You can see the predicted path doesn't change, it just gets longer, which means our prediction is actually fairly accurate and there's very little noise in it. If it was kind of like wobbling around or something, it would be not a very good prediction. But you can see our projectile trailing up towards this. And then our sphere is going to kind of overlap because the collision starts at the origin, not at the outside of the sphere. But then as we move into it, we get a hit, which means we have now hit our object, and all of that arc works and everything's fancy. So that's super slow, but if I want to do this super fast, like say 2,000, let's predict 2,000 meters a second. So this should hit it almost immediately. So we're going to do that same thing. We're going to pause it again. And then I'm going to start. And this will probably only be in frame for maybe less than 1. So it's going to be a big jump. And it's gone. But we hit. And so everything's still working. And we still do get the drop off way down there. Because this thing is really moving fast. So this way, you get bullet drop, hopefully realistic, and you can actually add wind physics or whatever, but it still works. So you can actually still hit objects and get, even if you fly through them in a single frame. We jumped a long way. 40 units. We jumped 40 meters in a single frame, and we still detected a hit. So that's just normal like Rigidbody or Raycast stuff. But if you did that with a Rigidbody and tried to actually like attach physics or enable physics on that, there's no way this would work. And doing that is really, really slow compared to actually just using Raycasts, because Raycasts are just nicer. So yeah, hopefully this gets your projectiles in your game looking a little bit more realistic. It gets that arc going or whatever else an effect you want. Maybe you want to like repel something or something and you want to calculate that. This gives you a way to do that. There's some abstractions that we could add in to make this a little bit better, but that's just, I don't know, fluff. It makes it nicer, but it doesn't actually enhance any of the principles. So I'm going to leave this here. Let me know what you think, and if you use this in your game, I would love to see it. But if you guys have any ideas for me, drop them in the comments below, and I will definitely take a look. I'm taking a new approach to how to do these things. I have an entire wall now dedicated to post-its that I'm putting these ideas on and just kind of picking them off as they sound interesting. So hopefully that makes it easier to kind of not only remember, but also just get ideas and kind of get them on the wall, literally in this case. That's about it for this video though. So till next time, see you, internet.